We've looked at how scale factors affect the lengths of similar shapes and how we can use the scale factor and the fact that the shapes are similar to work out missing dimensions. As you would expect, there is a different and slightly more complex impact on areas and volumes of similar shapes. So let's have a look at how that impact can be calculated and the kind of problems that you might face when scale factors are applied to higher dimension values. Let's look first at the impact on area. So our diagram shows two squares. So these are two similar shapes. One has sides of 1 centimetre and this other one has sides of 2 centimetres. If we look at the area of this, we can either do this by multiplication or by counting of squares. The area of the square with sides 1 centimetre is 1 times 1, or 1 centimetre squared. The area of the square with sides 2 centimetres is 2 times 2, which is 4 centimetres squared. So if we now compare the areas of the two squares, we can see that there's a scale factor involved there, not of 2 as we had with the sides, but a scale factor there involved of 4. So if we multiply the sides by 2, we've multiplied the area by 2 times 2, or 2 squared, which equals to 4. I'm sure you can probably see where this is going, but let's look at another square, another set of similar squares now. First of all, we've got a 1 by 1 square, and then we've got a 3 by 3 square. The area of the 1 square is 1 times 1, which is 1 centimetre squared. The area of the square with sides 3 centimetres is 9 centimetres squared, 3 times 3. So when the side is multiplied by 3, the area is multiplied by 3 times 3, or 3 squared, and that equals 9. I'm sure you will have seen the pattern by now, so I won't do any more squares. I'm not going to do a square of length 4 and a square of length 5. It's quite clear what the pattern is. Let's put all of the squares back up on the screen. So we have the square of side 1 and scale factor 2. The area is scale factor 4. With a square of side 1 and a square of side 3 with scale factor of 3, the area scale factor is 9. So if we extend that, we can get to a stage where we can see that when the side is multiplied by d, i.e. the linear scale factor is d, the area scale factor is d squared. That shouldn't be too much of a surprise, really. So if the linear scale factor was 4, then the area scale factor would be 4 squared, which is 16. If the linear scale factor was 10, then the area scale factor would be 10 squared, which is 100, and so on. Always best to make sure we understand something by doing an example. So here we have a triangle, triangle A, which is enlarged by a scale factor of 2. So the triangle A has sides 1, 2 and 2.24. What we've got to do is work out the perimeter and area of triangle B. First, let's work out the perimeter of triangle A. That's fairly straightforward. That's 1 plus 2 plus 2.24, that's 5.24. The area of triangle A is a half times the base times the height, or a half times 1 times 2. That equals 1 centimetre squared. So the perimeter of triangle B is the perimeter of triangle A times the scale factor, and the scale factor is 2. We're told that at the beginning of the question. So the perimeter of triangle B is 5.24 times 2 is 10.48. The area of triangle B, well, the scale factor, the linear scale factor, is 2. So the area scale factor is 2 squared. So if we take the area of triangle A times the area scale factor and multiply them together, we will get our answer for the area of triangle B. So that is 1 times 2 squared, which is 4. So 1 times 4 is equal to 4 centimetres squared for the area of the larger triangle. Let's have a look now at volume and the impact of linear scale factors on the volume of shapes. The diagram shows two cubes. The first cube has sides of 1 centimeters and the second cube has sides of 2 centimeters. The volume of the 1 centimeter cube is 1 times 1 times 1, which is 1 centimeter cubed. The volume of the 2 centimeter cubed is 2 times 2 times 2, which is 8 centimeters cubed. That's quite a considerable increase from 1 centimeter cubed to 8 centimeter cubed. So there we have two similar shapes and the volume has increased substantially. Let's now look at two cubes, first cube side 1 centimeter and the second cube sized 3 centimeters. The volume of the first one is, as we've looked before, 1 centimeter cubed. The volume of the 3 centimeter sided cube is 3 times 3 times 3, which is 27 centimeters cubed. I'm sure you can see the pattern already with this. When the side is multiplied by d, when the linear scale factor is d, the volume scale factor is d cubed. This shouldn't again be too much of a surprise once you've worked out that the area scale factor is d squared. It's not a huge leap of imagination to work out that the volume scale factor is going to be d cubed. Let's look at an example to make sure we've understood this. We're given a cuboid, and this cuboid has sides of 2 centimeters, 3 centimeters, and 3.5 centimeters. Those are the dimensions of the cuboid. So we can work out the total surface area of this cuboid and its volume. Total surface area we work out by adding up the surface area of each of the sides. So there's 2 tops, 2 bottoms and 2 sides. We work out the area of 1 and multiply that by 2. We get a total surface area for this cuboid of 47 centimeters cubed. Make sure you can see exactly where those values are coming from. There is another video on surface area that will help you to work out the surface area of cuboids. The volume is more straightforward. It's the height times the width times the length, or 2 times 3 times 3.5, which gives me 21 centimeters cubed. Okay, what happens now if the sides are enlarged by a scale factor of 2? If we're given another cuboid where the sides are 2 times as big as this? Well, surface area scale factor is the linear scale factor squared. So that's 2 squared, or 4. So the surface area of the enlarged cuboid will be 47, which is the original surface area, times 4, which is the surface area scale factor, and that gives us a total of 188 centimeters squared. The volume of the enlarged cuboid will be 21 centimeters cubed, which is the original volume, times the volume scale factor. The volume scale factor is the linear scale factor cubed, so that's 2 cubed. So this gives us a multiplication to do of 21 times 8, which gives us a total of 168 centimeters cubed. So for any given shape, as long as you know either the linear or the area or the volume scale factor, you can work out each of the others. The area scale factor is the linear one squared, the volume scale factor is the linear scale factor cubed. Once you've got that relationship okay in your head, you should be okay to work out any problems involving scale factors and similar shapes.